Okay, this is a much harder, hydrostatic force problem. We've got this semicircular dam. I know my picture doesn't look like it, but this is supposed to be a semicircle. Right at the water's edge, that makes it a little easier. Honestly, if it weren't at the water's edge, the only extra complication is we change our limits of integration. But we'll do this one. So just like always, we call our x-axis right here at the top of the water. Set our y-axis right through the middle, going down. So y goes down. Pick some random spot in the middle and call that y star or yi or some special y. And think about this little sliver right here. That's delta y thick. Y again is going to be our variable of integration. So we need, the whole key to all these problems is finding the area of that little sliver, and that will depend on y. It's delta y thick, but we don't know how long it is. The further down we go, the skinnier that little rectangle will get. So here is some distance x. Up at the top, x is 5. Down at the bottom, x is 0. We need to come up with an equation of this circle so that we know how big x is at some particular y. Well, if we just imagine a circle of radius 5, we know that has the formula x squared plus y squared equals r squared, 25. Remember, so this side here is x. I need x to be a function of y. Everything has to be in terms of y here. So we're on the top half of this circle here. I want to solve this for x and get x is the square root of 25 minus y squared. But this little rectangle here is 2x wide. So the area will be twice x time. Remember, area is length times width, so times delta y. And then force, that's area down here at y star. The force is always the pressure times the area. Pressure is rho GD, where D is the distance from the top of the water. So F star will be rho, the density of water, G, times our depth. Our depth here is y star, times 2 square root of 25 minus y squared. Now I've got force at some particular depth in terms of y. Then my total force is always the sum, approximately the sum of all those F stars, all the different little rectangles I could draw here. We take the limit as delta y goes to 0. That's the same as taking the limit as n goes to infinity, an infinite number of rectangles. And we get the integral. The total force is actually equal to the integral from smallest to largest y. This is a circle of radius 5, so this is y equals 0, and down here is y equals 5. Of rho g y to square root of 25 minus y squared dy. We should back down here. I left off my delta y on my area. This was the area right here. All right, now we just got to do this integral. So your first thought, you guys have taken Calc 2, your first thought might be, oh, this looks like trig sub. It's not. This is a simple just u substitution. If this is my d or my u here, then here's my du. So we do u is 25 minus y squared. Du will be negative 2y dy. So here is my du. Here's my u. We need to change our limits of integration. So when y equals 0, u will be 25 minus 0 will be 25. And when y equals 5, u will be 25 minus 25, u will be 0. So f total then, in terms of u, will be the integral, putting in my new limits. This one's on top, this one's on the bottom. The rho and the g, I'm going to go ahead and stick outside. Those guys there are almost du, but I need a negative. So if I put a negative in and take one out, that's my du. And I have square root of u. Now for simplicity, because I've got this negative outside the integral, I can fix that just by flipping over my limits of integration, flipping over my bounds. So I get rho g integral 0 to 25 square root of u du. Remember that is u to the 1/2 power. So the antiderivative, we raise the exponent up by 1 and divide by the new exponent. So I'll get u to the 3/2 divided by 3/2, so times 2/3, evaluated from 0 to 25. 25 to the 3/2 will be 125 times 2 will be 250 rho g over 3. And that's in newtons as long as we plug in 1,000 for rho and 9.8 for g. There's our final answer.